Hi everyone, welcome back to the part 2 of plus 2 chemistry, chapter 2 electrochemistry. So in previous class we have learned about electrochemistry, what is electrolysis, what is cell, and what are the two types of cell, electrochemical cell, electrolytic cells, right, and the function of Daniell cell, right, or the cell representation. So in today's class, mainly we are going to discuss about the standard hydrogen electrode and the Nernst equation. So by today's class, we will almost complete the 50% of this chapter. It's such a small chapter actually. We will also be including some questions from NCERT. Before coming to standard hydrogen electrode, in the previous class, that is part 1 of electrochemistry, I've missed a topic about the Daniell cell. We'll be discussing the same topic today, that missed topic today, and we'll be starting with standard hydrogen electrode. So in previous class, that is a part 1, the topic which I've missed to talk about is, consider two beakers. Here I have an electrode, here I have an electrode connected by voltmeter and a Daniell cell, right? In this setup, the potential shown for a Daniell cell is always 1.1 volt. Okay, the potential shown in the voltmeter or the voltmeter reading shown for a Daniell cell is always 1.1 volt. So, for example, here I am considering three cases. At the exam point of view, this topic is not much important, the topic which I am going to discuss now, but just keep it in mind, okay. So, here the potential of a Daniell cell is always 1.1 volt. I am providing an external potential, okay. So, we are considering three cases when external potential is less than 1.1 volt, when external potential is equal to 1.1 volt, when external potential is greater than 1.1 volt. We are considering these three cases for Daniell cell. We know that the potential of Daniell cell is, come on tell me, the potential of Daniell cell is 1.1 volt. So, when I am applying a potential which is less than 1.1 volt, what will happen to the Daniell cell? Think. Already for a perfect Daniell cell, the electron flows from anode to cathode and the current flows from cathode to anode. So what will happen if I apply an external potential which is less than 1.1 volt or less than the Daniell potential? Nothing will happen. The system will work as before. Okay. Now the second case is when applied potential is 1.1 volt, which is equal to 1.1 volt, which is equal to the potential of Daniell cell. What will happen to the system? Actually, in such a case, no reaction will take place, okay. No reaction will take place, which means that there will be no flow of electrons or no flow of current will be detected, okay. Voltmeter will show no deflection in such a case. When the external potential or applied potential is equal to 1.1 volt, no reaction will take place. Now, the third condition, when external potential is greater than 1.1 volt, what will happen? Think here, think. When it was less than 1.1 volt, what happened to the system? When it was less than 1.1 volt, nothing happened to the system, right? It worked as before. But in the case of greater condition, when external potential is greater than 1.1 volt, system won't work as before. It will work in a condition opposite to that when the system was applied with the potential which is less than 1.1 volt. When the applied potential was less than 1.1 volt, the electron flow was from anode to cathode and the current flow was from cathode to anode. But when I apply a potential which is greater than 1.1 volt, the electron flow will be from cathode to anode and the current flow will be from anode to cathode. That means the Daniell cell will reverse. The functions of the processing of Daniell cell will reverse when the applied potential is greater than the potential of Daniell cell. So that was a topic left to be talked about in the last part 1. Today we are going to deal with standard hydrogen electrode. What is standard hydrogen electrode or SHE? What is SHE? She or he? SHE means it's a device used in chemistry to determine the unknown potentials of species. I've been provided with magnesium, zinc, copper or anything, but I don't know the potential of that species. So as to find out the potential of that species, I use standard electrode potential, okay, SHE, the setup of SHE. So let's see how that's working so as to find the electrode potential of a species, unknown electrode potential of a species. So consider two beakers. Here I'm dipping a zinc rod. Here I'm using standard hydrogen electrode. This is anode, this is cathode. So remember, this isn't the exact structure of standard hydrogen electrode. The detailed structure will be discussed later in the same part itself. So here I've used zinc rod as anode and cathode. It is standard hydrogen electrode. So I need to find the potential of zinc rod using standard hydrogen electrode. How is it found out? We know the equation total potential or cell potential of a cell, the electrode potential of a cell or the cell potential is equal to E cathode minus E anode. Here cathode is She. So E She minus anode is zinc, E zinc. The potential of She is taken as 0. So from this we can tell that E cell, negative of E cell is equal to E zinc. The potential of zinc is equal to the negative of the cell potential, is equal to negative of the cell potential. So you might be thinking like, how did I choose 0, the potential of She as 0? So remember the process, the purpose of She. Remember the purpose of She which I told you earlier? The purpose of She is to find out the unknown potentials of species, right? So here the value of the potential of She is set as 0. The potential of She is set as 0, with which we can find out the unknown potential of the species. Okay, here it's only because the potential of She is 0 we are able to find out the potential of unknown species. Here it is zinc. So yeah, coming to other features of standard hydrogen electrode, it's a reference electrode. The reference electrode in the sense it is used to refer to the unknown values, potential values of species. It is its reduction potential is 0 volt at all temperatures, already discussed. It can act as both anode and cathode. If zinc is being used as cathode and She is being used as anode, no problem, the value won't change. Okay, so standard hydrogen electrode can be used as anode or cathode. Okay, no change will happen. So questions will come like explain She, explain the working of She, or what are the features of She, etc. So how is it helpful enough to predict or determine the unknown potential of a species? So you need to write all these answers. Now, representation of She, the cell representation. Before that, we need to know how She is constructed. Again, consider a beaker. In this session or in electrochemistry, we are full of beakers, right? Okay, consider a beaker, and we are using a platinum wire here, platinum wire, and which is this platinum wire is dipped in glass tube. At the end of the glass tube, we are having a platinum foil, So this is a platinum wire. This is a glass tube. This red thing is a glass tube, and this is a platinum foil coated with platinum black. Okay, platinum foil coated with platinum black. This is acting as catalyst here. Okay, this platinum foil is acting as a catalyst here. Now, the electrolyte which I am using here is 1 molar H plus. 1 molar H plus. 1 molar H plus is used as the electrolyte. Also, here I am having a small aperture through which at high pressure H2 gas is passed to the glass tube. H2 gas is passed to the glass tube. So through this aperture at high pressure hydrogen gas is passed to the glass tube. So this is the setup or apparatus of standard hydrogen electrode. It is having a platinum wire, it is having a glass tube, and it is also having a platinum foil which is coated with platinum bag, acting here as a catalyst. And through an aperture we are providing high hydrogen gas in high pressure, sorry, H2 gas, and also we are having here the electrolyte of H plus, 1 molar H plus. So let's try the anodic and cathodic reactions, right? Anodic and cathodic reactions can be well studied from this. At anode, what will happen? Yes, half H2 will be transformed into H plus and electron minus. In the case of cathode, the cathodic reaction will change to H plus electron minus gives half H2. When you see the cathodic and anodic reactions of standard hydrogen electrode, it is clear from this that the cathodic reaction is just the opposite of anodic reaction, or anodic reaction is just the opposite of cathodic reaction. Now, from this we are able to find out the cell representation of She. Here PT, H2 and H plus, PT, H2 and H plus. So this is platinum, this is hydrogen gas, and this is the electrolyte used, 1 molar H plus. So never forget to write PT along with H2 and H2 along with PT, because without PT being together with H2, or without H2 being together with PT, the oxidation reduction processes will not take place smoothly. So this is the cell representation of anode. So tell me, what's the cell representation of cathode for a She? Similar to the cell reaction of anode and cathode, cathodic reaction is just opposite of anodic reaction, right? We just wrote before. Similar to that, cathodic cell representation is just the opposite of anodic cell representation, means H plus, H2, PT. This is the representation of standard hydrogen electrode. Now, how would you determine the standard electrode potential of the system Mg2 plus and Mg? Okay, so here the question is asked to find out the electrode potential, or they are asking how are we going to find out the electrode potential. Similar to the way, yeah, we are using She because She is used for finding out the unknown potential values of species. Here the species is magnesium. So, magnesium is dipped in MgSO4 solution. Okay, here She is taken as anode because the voltmeter reading shows that the electron is flowing from a magnesium to standard hydrogen electrode. So definitely Mg will be the anode and She will be the cathode. Okay, anode, cathode. All right. So how would you determine the standard electrode potential? For that we need to write the cell reaction. Yeah, cell reaction means I meant the cell potential equation for cell potential. Equation for cell potential. Tell me the equation. E cell equal to E cathode minus E anode. Here E cathode is She, right? Here E cathode is She. So 0 minus E anode, E of Mg2 plus Mg. So how do you determine the standard electrode potential? They are asking about the standard electrode potential. So just E naught C, E naught A, here E naught. So negative of E naught cell will give you E naught of Mg2 plus and Mg. This is the final answer. This is the final answer for this question. Okay. Now, can you store copper sulfate solution in zinc pot? Right, in zinc pot. Is it possible? Is it possible? Let's see. Copper sulfate solution in zinc, right? So, zinc, when reacting with copper sulfate, what will happen? Zinc will displace copper from copper sulfate solution, and zinc sulfate solution along with copper is formed. Copper is released, zinc sulfate is formed by displacing copper from copper sulfate solution. So zinc is having high reactivity. Okay, high reactivity. So in such a case, can you store copper sulfate solution in zinc port? No. Zinc will displace copper from copper sulfate solution. So such a setup is not possible. We are coming to Nernst equation. Nernst equation. We have learned about She in detail. Now Nernst equation. A scientist named Walter Nernst found out the relationship between electrode potential and ionic concentration. Ionic concentration means the concentration of electrolyte. So what did the scientist Nernst do? The scientist has found out a relationship between the electrode potential and the concentration of electrolyte. And what was the relationship? Just remember the relationship in mind. The relationship is E cell equal to E naught cell minus RT by NF natural log concentration of metal, concentration of M divided by concentration of Mn plus. This is the equation found out by Nernst so as to have a relationship between electrode potential E cell and the concentration of electrolyte Mn plus. So that in such a case the relationship between electrode potential and Mn plus concentration of electrolyte, the concentration of metal, that is M, the section of M, the numerator is taken as 1. So equation can be modified. E cell equal to E naught cell minus RT by NF Ln 1 by concentration of Mn plus. This natural log Ln can be turned to logarithm log by multiplying it with 2.303. Ln will give you log value. Okay, 2.303 Ln is will give you log value. So this is a Nernst equation found out by the scientist Nernst, providing a relationship between the electrode potential and the concentration of electrolyte. Okay, concentration of electrolyte. Here, I've already told you in this equation, this is the electrode potential, this is a standard electrode potential, and this is a concentration of electrolyte. Now, tell me what is RT by NF? RT by NF. R is actually universal gas constant. Gas constant. Universal gas constant. T is the temperature. Those are constants, okay? All these are constants. F, Faraday's constant. Faraday's constant. And N is actually, it's not a constant, it's just the number of electrons. Number of electrons. These three are constants. RTF, universal gas constant, temperature and Faraday's constant is constant. So that is the value of the constants. Constants are 8.314, which is a universal gas constant. Temperature is 298 and Faraday's constant is 96,500. Substituting those values, the equation is modified into, electrode potential equal to E naught cell, standard electrode potential minus 0.059 by N log, not the natural logarithm, this is the logarithm, 1 by Mn plus. Okay, this is the equation, the modified equation of Nernst. Now, shall we find out the equation for Daniell cell, the Nernst equation for Daniell cell? Shall we? Okay, yes, we can do it. So we are going to find the Nernst equation for Daniell cell. Here Daniell cell, we already know that E cell equal to E cathode minus E anode, right? E cathode minus E anode. Here the cathode is copper 2 plus copper minus E of potential of anode, zinc 2 plus and zinc. we need to find the potentials first. So E of cathode equal to E naught cathode minus 0.059 by N. N is actually 2. In this case, N is actually 2. See, 2. Okay, N is 2. N is 2 and log 1 by concentration of the electrolyte, that is copper 2 plus. Now coming to anode section, E anode equal to E naught cathode, E naught anode minus 0.059 by 2 log 1 by Zn2 plus. Zn2 plus is the anode. So putting these values in this, we'll get the overall cell reaction equal to E naught cell minus 0.059 by 2 Zn2 plus by copper 2 plus. Concentration of copper 2 plus and concentration of Zn2 plus. This one. This is the Nernst equation for Daniell cell. Nernst equation for Daniell cell, which is E cell equal to E naught cell minus 0.059 by 2 Zn2 plus, concentration of Zn2 plus divided by concentration of Cu2 plus. Nernst equation for galvanic cell, as we already discussed. Represent the cell in which the following reaction takes place. We need to represent the cell, that means we need to write the cell representation. Mg plus 2Ag plus gives Mg2 plus plus 2Ag. So how are we going to represent this? First the anode, right? Here oxidation is taking place for Mg. Mg is getting oxidized to Mg2 plus. So it is an anode. Mg. The anodic solution may be magnesium sulfate. So Mg2 plus is the ion. Salt bridge. The anode is Ag. So anodic solution and anode. This is the cell representation of the given reaction. Now, coming to the second part of the question. Calculate its E cell potential. How are we going to find its cell potential? Using Nernst equation, obviously. E cell equal to E naught cell minus 0.059 by N. N value is actually 2 here. N is 2. Log the concentration of product divided by concentration of reactants. So the product is here Mg2 plus, concentration of Mg2 plus divided by Ag plus twice. Okay, twice. So this is the equation. Substituting the values, you will get E naught cell is already given 3.17 minus 0.059 by 2 log Mg2 plus is already given, the value is given here 0.130 divided by Ag plus 0.0001 whole square. So when you substitute the values and calculate it, you will get the final result. Okay, this is the equation. Now, relationship between equilibrium constant of a reaction and a standard potential of the reaction. Okay, the relation between standard potential and equilibrium constant. Consider a reaction A moles of A plus B moles of B gives C moles of C plus D moles of D. Here I am writing the Nernst equation for the same reaction. E cell equal to E naught cell minus 0.059 by N log concentration of products divided by concentration of reactants. So, C to the power C, D, concentration of D to to the power D, and concentration of A to the power A, and concentration of B to the power B. This is actually the equilibrium constant. Log Kc, this will become, this part will become log Kc. Because we have already learnt in the lower classes that the ratio of product side and the concentration of product side and the reactant side will give you the constant, equilibrium constant. So this is log Kc, and here it will become 0.059 by n log Kc, which will be equal to E naught cell. Because why is it equal to E naught cell? Here E cell equal to 0, E cell equal to 0, or cell potential equal to 0, because the condition is equilibrium. We are taking the relationship between equilibrium constant and the electrode potential. So the status of setup, or the condition of setup, will be in equilibrium. In equilibrium, there is no net flow of electrons or current, or reaction won't take place. So the potential, cell potential equal to 0, E naught cell equal to 0.059 by n log Kc. Hope the equation is clear. Now we have a problem here. Calculate the equilibrium constant of the reaction copper plus 2 Ag plus copper 2 plus 2 Ag. Okay, so we are asked to find the equilibrium constant. We know the equation, E naught cell equal to 0.059 by n log Kc, log Kc. So the values are already given in the question. E naught cell is 0.46. Taking to the left side, it will get multiplied with E naught cell. N is actually 2. N is actually 2 into 2 divided by 0.059 when it is taken to the left side will give you log Kc. From this value of log Kc, just anti-log it. How are you going to anti-log it in calculator, scientific calculator? How are you going to anti-log? Shift plus log will give you anti-log of a value. So anti-log the value and you will finally get Kc. You will finally get the value of Kc. So don't waste your time. Go and learn the previous parts, the part 1 and 2. And I'll be back with the part 3 of the same chapter, electrochemistry, very soon. So with that span of time, you must learn thoroughly the first 2 parts of electrochemistry. Yeah, bye.